And you have inevitably come across, you have been asked to find out say the transfer function. Just a moment. Initially you were asked to find out say Laplace transform of say 1 by s, 1 by s plus a, and then you moved on to more complicated stuff like now when you look at textbook problems, in most of the cases you will find that when you are given the transfer function, they are like pretty easy looking. You have, in many cases you will find them um, well factorized actually. Now one of the problems that we have to face is, one, we have a polynomial in S. So we have a polynomial in S, and when we want to find out Laplace transform of something involving such a polynomial, you are doing factorizations, which essentially means finding the roots. This is one thing that you have been doing. Second is, you have say a system which is defined by some, oh Jesus,
Sir, you are muted. We can't hear.
muted me.
Yes, sir. Yes, sir.
Yeah, okay. So I'll repeat what I've been saying. Um, Please avoid doing this. I mean, like, I normally don't try to take a full control of a class so that I can interact with people, but it will be unfortunate if I have to. So again, I'll repeat that when you have been doing, and please prompt me if you don't get to hear me or see what I'm presenting on the screen. So what I was stating is you have been dealing with this kind of stuff. You have been doing the Laplace transform of this and this kind of stuff, then moving on to complicated stuff like this. And what you have been doing is you have had to deal with factorization of a polynomial in S like this. What does factorization mean? Factorization means you actually are finding out the roots of this polynomial. On the other hand, you must have also had a situation like this where you have some input, and by this time, correct me if I'm wrong, you must have done something like this, having a feedback. So in this case, what will be the output like? You'll have a transfer function of the form
Sir, there is a video lag, sir. Like we can't see the drawing of the drawing you are drawn on the board.
Yes, please.
Sir, like there is a lag in the video. We can only see the transfer function in the diagram.
Till now, that feedback has not yet come.
The figure has not come.
And yes, only GS is there, comparator is there, the feedback loop is not complete.
But this is, I'm just using it on my local computer. So can you see now 1 plus GSHS?
No, not even the drawing. Forget 1 plus GSHS. Not even the drawing is complete.
Okay, let me just log in and log out. Is the screen visible now? Can you see the screen now? Hello?
Yes, yes, sir.
Yes,
Okay, and is it
Yes.
updating? Can you see this full block diagram?
Yes, sir.
Okay, so when you have this, in this case, you have a problem that even if you know GS fully defined for you, you don't get to understand the full nature of 1 plus GSHS. This is going to form a new polynomial. So even if you are aware of how to factorize this, you wouldn't be knowing how to factorize this and get your roots. Now, why is the finding of these roots important? This is because if you are looking at, let us say, a factor of the form S plus A, in that case, you are going to get S is equal to minus A, and the sign of S, A will tell you whether it is going to be positive or negative. You can also have factors of the form S square plus AS plus B. So if you consider what is going to happen when you are going to factorize this, first is, if you have any one of A or B negative, then there is a possibility that you will be getting you can get complex conjugate roots with real positive part. You can also have if you have S square plus AS plus B with AB both positive, in that case you are going to land up for sure with complex conjugate roots, and they will have and in that case, if you consider, say for instance, consider something like S square plus S plus 1 is equal to 0. So what will you get? you will be getting S is equal to so you have now having this kind of roots is good, because in that case, if you can remember your Laplace transform, you will see that this will contribute to an oscillatory part of the signal, whereas this is going to contribute to damping. And if this is minus, then it means your system is going to decay with time. And when we do this factorization, you will find that you are mainly landing up either with a single factor like this, or you are landing up with something like this, where you can't factorize into factors of this form. When you have A or B negative, then that possibility does exist, that you are going to be able to factorize this S square plus AS plus B into the form S plus C, S plus D. Now, let us look at what these different kinds of roots will result in. If you have in your polynomial so that means you are going to have a root here like this. This will result in a time response which looks like this, something constant. Then we can consider roots of the form plus minus j omega. So both the roots are lying on the imaginary axis. So here, when can you get roots like this? When you have S into you have a polynomial like this. This kind of roots will result when you have something of the form s square plus a square. So note here that in this case you have a quadratic with one term missing, and in this case you are going to see a steady oscillation. So this does not look that much harmful. This is also, well, as we will see that this is neither good nor bad. It means that when your system in a polynomial, we have a root like this, then the system will always be oscillating any disturbance that is not going to die down. It is simply going to persist, but it is not going to grow. Now we can have a root like this. So what we'll see in this case is a response that is continuously decaying. If on the other hand, if I have a root like this, so when are you going to have a root like this? When you have a factor of the form s plus a greater than 0. When you have a factor of the form s minus a, once again a greater than 0, then this is what you are going to see in your response. So this is good. This is bad, because it means if you have this, an input to the system can result in an output that is going to continuously increase. So we definitely won't want our system to result in a polynomial that has roots like this. This is permissible. Next, we can have a situation and this will happen when we have quadratic factors, where we have complex conjugate roots, but they are on the left hand plane, left hand side. That is, in such a case, you are going to have a response like this, which is going to decay with time. So this again is a good type of response. What happens, and this will happen when you have
Sir,
yes,
sir, like there is a very big lag between the writing and the explanation, sir. Like we can hear the audio very well, but the on-screen drawing and the writing is not at all visible at the
I
time of
don't know, there
delivery of
must be
speech.
some problem with my network then.
It's coming, but just like delayed. That's all.
Can you see these now? Root with s is equal to 0.
No, sir.
No.
Um, okay, let's have a couple of minutes break. I'll just check my network and again redo this thing.
Kingshuk,
Huh?
Kingshuk,
Yes.
if you are drawing in a screen,
Hmm.
if you move up and down little bit, or go to another window and come back, then it refreshes. If you are in same window and writing, then it doesn't refresh. So
No,
if
but
you
I have
scroll,
been taking these classes.
yes, if you take
Similarly,
scroll it a little bit, it will refresh.
okay, let me just change the network and see whether things improve. Can you see my screen now?
Yes, sir.
Yeah, okay, I'll just do some. Is it updating?
Now it's updating, sir. Yes.
Yes, sir.
Okay, fine. So, just a moment. Okay, so what I have been describing is basically what happens. One, if you have in your polynomial, if you have s into something like so in this case you are going to this is where your root will be and your time response is going to look like this. This is okay, sort of. The second case that I described was so when can this happen? You have two roots, imaginary, and they don't have any real parts. So you have a factor of the form s square plus a square. And when you have this, you are going to see a response like this, a response that is not going to die down. So this again is neither here nor there. We really can't say whether they are good or bad, they are somewhere in between. Then we have, please let me know if it's working okay now.
Yes, sir.
Then we
It's
have
working
this,
well.
yeah, then we have this kind of a situation where you have a root here, which means you have a factor s plus a is greater than 0, root is negative. In that case, you are going to see a time response like this. This is definitely good. then you can have factors of the form s minus a greater than 0. Your root is here. This is definitely positively bad. We don't like this. Having factors and roots like this.
Sir,
Yes?
sir, the real part we are talking about the positive, the damping or the amplification. So what about the sign of the imaginary part? Is it for the phase?
Okay, if you have 1 by s plus a, you tell me what are you going to get? Laplace transform.
It is e to the power minus a t.
Yeah, so now if it is, I mean like 5 into s plus a or 500 into s plus a, we are not really bothered. Or even if it is minus 500 into s plus a, what will happen is that maybe it will start from here, but it is going to come down all the same. So this phase part is not going to come into picture here right now. I mean, when you are talking of phase, we are not dealing with these linear factors. Because in these cases, see where are the roots going to lie? 0, pi, pi by 2, 3 pi by 2, that is it. Now, if you have roots like this, so in this case, when we look at roots like this, both are having negative real parts. And these things can happen as I have shown in an example, that you have s square plus as plus b in this case you are going to see nice things again. There will be oscillations, but they are going to die down. On the other hand, if you have stuff like this, not good at all. You are going to see small things becoming bigger and bigger with time. There will be an exponential growth. Very bad. This is actually quite good. There can be certain other cases also which can be like which means I have sorry. And when you have this, you are going to see a response which will look like this. Not good again. We can also have situations like this. In which case you will have an output which is growing,
Sir, why will it grow for the second case? That is normal sinusoidal wave, right? Like the output is sinusoidal.
in this case, see, you are having a square plus a square whole square. I mean, when will you have two? These are not two roots only. They are four roots actually, but they are coinciding. Double roots. Here we have double roots out here in the origin. When you have a single root at the origin, then what happens? You get a flat line. The double root adds to this linear growth. So this doubling of roots, when you have purely imaginary roots, but you have roots like, let us say, minus I plus I. So when can you have that? When you have a factor s square plus 1 in your polynomial. But what about s square plus 1 whole square? So that is when,
Yes, Kingshuk.
Hmm.
Kingshuk?
yeah,
Yeah. So, students, if you remember, we did step function. Its Laplace transform was 1 by s. Ramp. Ramp means linearly increasing with time. Its Laplace
1
transform
by s
was
square.
1 by s square. Right. So, double roots at origin implies ramp. It will continue to increase with time. The same case applies when you have four roots, okay, where
Yeah.
two of them are same and complex conjugate.
In fact, you have seen this kind of responses earlier. I will just mention one thing, and this is something that we tend to forget. If I give you a differential equation, let us say, just a minute.
Take x double dot is equal to constant. That's it. X
yes.
double dot is constant, velocity response grows. That's it.
No,
Displacement
no.
response grows.
There's another possibility also. Let us say X, where I think they'll be recalling something that they often miss out. F, say you have a input F cos omega t. So you people are familiar with the solution to this? It will be some amplitude k into cos omega t. But what happens when omega is equal to omega n? This is something that is taught to you when you are initially taught solution of ODEs. In that case, you will have, when you consider the full solution, you will have one part which will be of the form a cos omega t, and you will also have a2t cos omega t. So when you have a resonance like condition also, then you can have such a situation where you have a oscillating function continuously increasing. The difference between our usual instability is that this oscillating function, if you have it, then oscillating function grows exponentially. When you have a case of resonance, you have an oscillating function in time whose envelope is linear. So this is an example, another example where you can get when you have encountered situations like this. So this is more or less covers the different, almost all the different types of roots. Yeah, I have missed out something. That is, since we have already discussed roots in the on the real axis, single root. So if you consider what happens if you have a double root, in that case, you are going to have a response looking like this. Whereas you have a situation like this. Again, bad. This is reasonably good. I mean, like, it's going to go up and then it's going to come down also. So our basic conclusion is that from here, that when we factorize and find roots, those roots should not have real positive parts. Real positive part is bad. In fact, having if you consider even 0 as a positive, I mean, like, if it is purely imaginary, even that is not that good. First of all, there can be a case of doubling. Second is, even otherwise, they will result in either an unchanging disturbance or an unchanging signal. If you get a disturbance of some sort, this is kind of indicative that the disturbance is simply going to be there. You don't want to sit on a sofa which keeps on bouncing you continuously, not a very comfortable feeling. You want that thing to settle down after a while. So let us now after this summary, consider what is our basic problem. Our basic problem is, then when we get a polynomial, we have to look at the roots, and then we have to determine whether the roots have a real positive part or not. Okay? Now, our major problem is here. I will like to have a short question and answer session with you people. Very simple questions. So if I give you a function y is equal to ax plus b is equal to 0, a linear equation, you can immediately tell me the root, right? It will be minus b by a. Say 3x square plus 4x plus 5 is equal to 0. Can you find the root? A yes or no will suffice.
Yes, using that quadratic formula. Yeah.
Exactly.
And it will be
And you get a
possible
closed
cubic
form
and
solution.
quadratic. Yeah.
And you get a closed form solution. So it means that if you have an equation ax square plus bx plus c is equal to 0, then suppose you are varying a or b.
Sir?
Yes.
So only your MS Teams window can be seen in the middle of the screen.
Yeah, now I am not writing anything. Okay. This is just a discussion between us. So the thing is, when you have ax square plus bx plus c equal to 0, now you can keep, let us say, a and c as constant and vary b. And if I give you an assignment, they're all right. I have given you a certain a and a certain c. B is something that varies. What are the nature of the roots? How long will it take you to submit this assignment? If you have MATLAB at hand, or let us say, you don't use special functions of MATLAB, but you can quickly do it because, as you know, you have the solution. We can go up to cubic also. You have done solutions of cubic equations, I presume. Yes, no.
Not officially.
What
But
do you
like,
mean?
yeah, cubic and
Mechanics of-
biquadratic can be solved using formulae. I know that degree 5 cannot be solved. And
Yeah.
as in, like, it has not been
Yes,
taught in any
exactly.
course. That's all.
You have been able to do cubic equations in your mechanics of solid classes, maybe vibrations. There is something called quadratic equation also you can solve. Problem starts with x to the power 5 onwards.
So you need group theory, etc. Like,
Whatever you do, you can't get any answer.
yeah.
Exact answer, a closed form answer. So that means when you have a polynomial from degree 5 onwards, you just can't find out the root and then, check out its nature. So we have to kind of get an idea of the nature of the roots without actually being able to solve for them. And this is where all these things started. Now that you have very good computers and pretty robust algorithms, you can find out roots of all kinds of polynomials, more or less. Especially polynomials is not that much of a problem. I think you have an algorithm called Bowden's algorithm which does this, including complex roots. But again, the problem is you really don't get to understand how the roots are going to vary with a particular coefficient, let us say. So this is where all these things started, that how to be able to predict whether a polynomial has a root with a real positive part without actually solving for the roots, and how to predict also the nature of this root with variation of certain parameters, say certain coefficients to the polynomial. So we are now going to work on something that solves part of the problem. That is the Routh-Hurwitz method or criteria or whatever you call it. Here we cannot actually get a variation of the roots, but this is the first step that we can say whether there is a real positive part, a root with a real positive part or not. And they will obviously happen if it is a complex root, then they'll happen in pairs. Otherwise, if it's a single factor, you can have simply s is equal to 5, s is equal to 2, something like that. But this allows us to predict for any polynomial whether there is a root with a positive part, and therefore we can predict whether our response is going to remain within bounds or it is going to become unbounded. So now we'll have to look at the properties of the polynomial itself, some basic properties. I have given you a simple example earlier. Where if you have x square plus x plus 1 is equal to 0, so what did we have out here? And this is going to be an important criteria that we look at. First is, if you have we are getting so this is what we obtained. Now, if you have x square minus x plus 1 equal to 0, or you will recall in some of these cases you will be able to factorize easily, or you will get a root with a positive part. See, if your b is positive, for instance, a negative, then that itself tells you that you are going to have a real positive part, and real positive part is not something that we want. So first of all, when we look at a polynomial, we have to check Why have the same sign? Because I mean, like, you can have something like sorry. So the minus can be taken out, and this does not change the nature of what we are trying to to find out. So if in a polynomial we check and find all the coefficients of the same sign, then right now we do nothing about it. But if so this is, even without applying this Routh criteria, this is something that you can predict. So when we have in a polynomial a sign change in the coefficients, then that means you are going to face instability if this polynomial is the result of your analysis of the system. You can also have missing coefficients. Simplest example, what do these result in? So these will result in this case you will have s square equal to 7, and in this case you will have s equal to root 7. Here you are going to have s is equal to plus minus root 5i. So either you are going to have continuous oscillation or you are going to have an exponential growth. So this missing coefficients, this logic extends even if you have something like s to the power 7 and all of a sudden s to the power 5 is missing and you have 3s to the power 4. Even another missing coefficient is simply this. So here you will have s is equal to 0 as a root. So whenever you have coefficients missing, or when you have non-negative, when you have change in sign of the coefficients, then you can straight away say that you are not going to have a system that you like. You are going to have instability in such as when you are dealing with a system which results in such kind of a polynomial. So we can't predict. So two bad cases are and when you have all coefficients having same sign, it is can't really say. And this is where Routh-Hurwitz comes in. So let me just explain this criteria. It will remind you a little bit of cross multiplication, but it's a special kind of cross multiplication. Let me take a polynomial . So first what I'll do is, highest coefficient is 3. So I'll write here SQ. Next coefficient is S square. Then S to the power 1. And finally we'll finish off with S to the power 0. I am not giving you people a very theoretical verbose explanation, because it is easier to understand this thing through numerical examples. So first I write down, since this contains 3, so the first column I'll write 1 out here, and this column, if it starts with 3, then it will contain all the coefficients which have odd powers. So this 1 here, 1, and this is 0, so it's not odd, so we end here. Then S square is minus 4, and this is S to the power 0, which, well, mathematicians will debate whether it's even or odd, or real or natural, but for us it's even. So this will be 6 into S to the power 0. Now the cross multiplication that we do goes this way. This into this minus this into this, and it is not like this. For the next number that we will generate, we will have to do a cross multiplication like this. So here look at the cross multiplication. I'll have to do a bit of erasing. We'll need some space. So I have s to the power 1 out here, and I need to fill up this part. How do I do it? You have a minus sign outside, and then 1 into 6 is equal to 6, minus 1 into minus 4 plus 4, and divide by this. So this will give me 2.5. If you do this exercise for the same thing, then this will be again 1 into 0 1 into 0, 0 into minus 0 into minus 4 divided by again minus 4. So the cross multiplication goes this way, divided by the first column of the lower row. So I'll get which will obviously be coming out as equal to 0. So this is my S1 and this is my S0, which I will form in a similar fashion, but now by using this. So I'll be getting minus 0 minus divided by 2.5 which will be equal to 6. These will come out as equal to 0. So you see, I have first of all, I need not have even attempted to do this, because this minus 4 already has a negative coefficient, but even otherwise you see that we are seeing a sign change out here, 1, then negative, then positive, positive. So how many sign changes do we have? One sign change from here to here, another sign change from here to here. So if you have two sign changes, then That means we are going to have two roots in the right side of that Argand plane or the complex plane. And if you look at the actual roots, you will find that the roots are so we are going to have roots with positive signs, which is not good. We can, I'll now give you basically let us have a look at how to write this table. If, let us say, I have a polynomial of the form then this is how my route table will look like. First I'll write S4, I'll put in A4, A3, A2, A1, sorry, A4, these will appear, yeah, A4, we'll begin with A4 because S4 is the highest power, then this will be A2, and then we'll have A0. Then, let me just space them out. So, then we have S cube, and corresponding to that I'll have A3, A1, 0. Now this is how the cross multiplication goes. First, you have the A3 down, then you have A4, this is your determinant with a negative sign preceding, and this, let us say, is equal to B1. Then when forming this determinant, you will take this and this, not this and this. divide again by don't forget the negative sign. So this, let us say, gives us B2. Then again the first column remains intact, and we have already tackled this column, so we have to kind of imagine that there is a, to make this up, we can simply put in 2 additional zeros out here. And not forgetting to divide by A3, this will of course come out to be equal to 0. When you are forming S1, again our logic will be the same, but we will just move one row down. So I'll have A3 A1 B1 B2 minus sign and divide by B1. So let us call this as C1 minus sign
Sir, what if A3 is 0?
what if
A3 is 0.
who's that name?
Manjunath, sir.
You were there in my kinematics class, Manjunath?
Yes, sir.
Yeah. Well, I shall answer that question in the next class. And that is a very good question. In fact, that is why we are going to have 2 classes on Routh-Hurwitz, because those are called special cases. And they will be resulting from where you have double roots on the imaginary axis. They are going to create this kind of problems, or missing coefficients. So those odd looking cases, they are going to result in some special tactics that we will use to do with the manage with our usual Routh construction. Though of course there is a way out. I mean, like I can tell you very simply that if A3 is 0, you don't take it as 0. You just take it as 1 in 10 to the power minus 1. Effectively, that is what we do. You will see that and do our calculations. There is another method also for tackling such cases, but we will discuss that in the next lesson. So anyway, let me finish this. So this will be equal to C2, this will be equal to this will be coming out equal to 0 straight away, so we don't need to bother about that. So this will be equal to 0. And this will be equal to 0 as well. And finally, we will conclude with the S0. So S0 will be again B1, C1, the first row. We have now moved to these are our these two will be our top rows now for this determinant, and we'll have B2 0, divided by C1. This will be a new coefficient D1, and these will come out to be equal to 0. You can calculate and check. So this is the algorithm that you start writing down with the highest power. If it is s to the power 5, your first row is s to the power 5, second row is s to the power 4, and so forth. And then you have these alternate coefficients. That is, if you are starting with a odd power, then your first row will consist only of the coefficients of the odd powers. Second row will consist of the coefficients of the even powers. If your highest power is even, then the reverse will occur, and then you do this cross multiplication pattern and check for sign changes. Now, before concluding today's lecture, as one of you has pointed out, you can have a case of one of the coefficients, these elements becoming 0, and that is going to create problems because you are going to divide by at some point or other by any component of the first column. So if that happens, then there has to be, we have to figure out some way out. So there are two ways. One is by considering the limit, other is also there. You can take something called a reciprocal polynomial, and you can also have cases where everything in a row becomes equal to 0. We can also, by looking at this route table, we can also predict straight away. It's not only a case of how many will be on the right hand side or left hand side, how many roots will have real positive parts, how many will have a negative real part, how many will be simply oscillatory. All these can be figured out, and this, as I said, this is our first step. Once we climb the staircase of route, then our next step that we will take is something called root locus. So here we can only say positive, negative, good, bad, okay, and we really don't have an idea of how good or how bad. There is a kind of way, but it's not really, it's called, like finding out what is known as relative stability through route, but it is not really, it doesn't give you a very quantitative feel of how good or how bad it is. For that, we have more techniques, and that involves one of the very straightforward techniques in a sense is the root locus technique. You can figure that out by simply considering, say, a quadratic equation, say x square plus ax plus 1 is equal to 0. So plot the roots as a function of a. A is, you vary a and plot it. So this is your first introduction, and what you will see is this finding out this root business and the limitations that we have of theoretical options of finding out the roots of a polynomial. That is what has led to multiple ways of analyzing this polynomial without actually finding out these roots. We have studied one, we'll maybe study 2 or 3 more depending on how much time that we have at hand. Also, another point that I would like to make out here is, as we move into complex domain, please remember that so far when you have drawn graphs of functions. You could draw them on a piece of paper, because you had y is equal to x, y is equal to ax square plus bx plus c or whatever. So you had an x-axis and a y-axis. This is another thing about the complex, about control systems, where we deal a lot with these complex numbers. We not only have complex numbers, we have complex functions of complex numbers. And you can't plot them on a piece of paper, at least not through a single drawing. So that is another aspect. As I said, that our inability to find roots of a polynomial exactly in a closed form sense leads to certain theories, and our inability to represent a complex number on a piece of paper. As human beings, we are used to visualizing things in 2D, not in 3D. So that has also led to certain theoretical developments. As we go further, you will understand the significance of what I am saying right now. So that will be all. My apologies for this disturbance in my network. I think from tomorrow onwards, I'll have to manage with my other router and things should work. Thank you all.